Hey, Dico. Welcome to Med Decode. It's become such a common thing. You're driving, the phone rings, you tap the Bluetooth button on your steering wheel, and you feel totally safe.
Of course. Because the logic is my hands are at 10 and 2, so I'm in control.
Exactly. We've all sort of accepted that hands-free chatting is the safe way to handle distracted driving.
It's a really comforting myth, but it's a myth that today's deep dive is, well, going to completely shatter.
Right.
We're looking at research that really dissects what's happening inside your brain, more importantly in your eyes, when you're talking while driving. This study we're analyzing today shows the danger isn't your hands at all. It's cognitive.
So our mission today is to unpack that. This shocking truth that the conversation itself is stealing resources from your brain, and it's compromising the most fundamental part of driving safely, or as the summary for this paper put it, just a shit a day.
And that's really the foundation of safety, isn't it? Your gaze behavior. So how quickly and how accurately your eyes find and track things, that provides almost 90% of the information you need to drive.
90%. Wow.
So if that first primary system is degraded, everything else, like hitting the brakes or steering away, is already way behind.
Okay, so let's start with that big misconception. Most people, I think, assume the danger of a phone is purely physical. You can't steer properly or shift gears.
And they believe that hands-free technology just solved the problem.
Right. But the data says otherwise.
Completely. The data shows pretty consistently that the crash risk stays alarmingly high. It doesn't matter if the phone is in your hand or on a mount.
And how high are we talking?
We're talking about a crash risk that's roughly 4 times higher than normal driving.
4 times.
Which, to put that in perspective, puts it in the same league as driving under the influence.
So the science is really clear on this. The physical act of holding a phone it's irrelevant to the risks.
It is. So if it's not our hands, we have to define the real culprit here, which is cognitive load.
And what exactly is cognitive load?
It's just the amount of mental effort your brain is using at any given moment. I mean, driving itself, especially in traffic, is already a high-load task. You're perceiving, making decisions, and controlling the car all at once.
And then you add conversation on top of it.
And you force a huge amount of your brain's resources to switch over to language processing.
So when you're actively trying to form a thought or understand what someone else is saying.
Exactly. When you're organizing thoughts into speech, these high-level executive functions in your brain are working overtime. And here's the critical part. They are the same resources you need to process a complex visual scene and make quick, accurate eye movements.
So it's not just that you're tired. It's a specific direct conflict in your brain. It's like 2 essential programs trying to run on the same tiny processor at the same time.
That's a perfect analogy. The research paper called it a conroar, a fierce competition for those limited brain resources. The conversation isn't just a background distraction. It is actively robbing the fuel needed to see and react to the road.
And the conversation wins. Your reaction time loses.
Every single time.
Okay, this brings us to the actual experiment, which had a really elegant design to isolate this exact effect.
Right. The study by Suzuki and his team, they didn't even put people in a driving simulator.
No, they stripped it all the way back. They focused purely on the motor control of the eyes.
They used a center-out eye movement task.
What does that entail?
Well, you have participants look at a central point on a screen, and then a target flashes briefly in one of 8 positions around it, and their job is just to shift their gaze to it as quickly and accurately as possible.
So it's a very clean way to measure the speed and accuracy of those super fast eye movements.
The fastest motor movements in the body, yep. The saccades.
And they tested this under 3 different conditions. The first was just the control.
Right, just do the eye task. That gives you a baseline for how fast and accurate a person is normally.
Then condition 2 was listening. This is a big one for anyone who listens to, audiobooks or our deep dives while driving.
Here, people just passively listen to a Japanese novel, I Am a Cat. They were told to focus on it and understand it, but crucially, they didn't have to speak.
And then the last condition, the one designed to really crank up that cognitive load.
That was the talking condition. Here, they had to actively answer questions. Some were about memory, like, when did you sleep last night? And others were general knowledge, like, where's the capital of Italy?
So what did the baseline show? What happened when people were just listening?
This was the really crucial context.
Yeah.
The listening group showed almost no significant difference compared to the control group.
So just passively taking in information, even complex information.
It doesn't really interfere with your gaze control in a meaningful way.
Okay, so that's the good news. But what happened in the talking condition?
Well, the moment they had to start forming answers and speaking, their performance just fell off a cliff. The interference was immediate, and it was measurable across every single metric of eye control.
Okay, let's break down those milliseconds, because this is where you can really see the danger. The researchers looked at 3 different parts of the eye movement.
Right. The first one is reaction time. This is the decision part. The time from when the target appears to when your brain actually sends the command to your eyes to move.
And what happened there?
In the talking condition, that initial step, just noticing and deciding to look, it tended to be longer. A driver is simply slower to even begin to notice something has changed.
So that's the first delay. What's the second component?
Movement time. This is the physical action, the time it takes for your eyeball to actually travel from the center to the target.
So this measures the raw speed of the eye.
And this is where you really see the sluggishness. Movement time jumped significantly. It averaged about 260 milliseconds for the talking group, compared to only 150 milliseconds for the other 2.
So that's over 100 millisecond delay.
Yes. And if you translate that to a real-world scenario, say you're on the highway going 65 miles per hour, that tiny fraction of a second means your car travels another 10 or 11 feet before your eyes have even finished moving to where the hazard is. That's a lot of ground to lose.
That lost distance adds up so fast.
Yeah.
Okay, so what was the third component?
Now, this is probably the most dangerous one, adjusting time.
Adjusting time.
It measures how long it takes for your gaze to settle and stabilize once it gets to the target area. It's a direct measure of the accuracy of that initial eye movement.
And this is where the data gets kind of wild.
It's stunning. In the control and listening groups, it took about half a second to stabilize, so 500 to 550 milliseconds.
Okay. And when the brain was busy talking?
It soared to an average of 1,226.5 milliseconds.
Wait, over 1.2 seconds.
Yes. It more than doubled the time needed to get a stable, clear look at the target. It means the brain sent a sloppy, imprecise command. The eye overshot or undershot the target and needed over a full second of corrections to lock on.
A full second just to get your view stable. In traffic, a second is an eternity.
Absolutely. You could miss a car braking, a light changing, all because your brain is busy cleaning up the messy eye movement it just made. The cognitive load doesn't just slow you down, it makes you sloppy.
But the study found something else too. Something about the direction you're looking. It turns out we aren't equally quick at looking in all directions.
That's right. There's an inherent saccadic bias. As humans, we are just naturally a bit slower to react to targets that appear in our lower visual field.
So things appearing down, toward the ground.
Exactly.
Yeah.
Compared to targets in our upper field of view, it's just a built-in human limitation. We're already at a slight disadvantage for things happening near the ground.
Which is where a lot of immediate road hazards pop up.
And this is where the cognitive load from talking creates this perfect storm. The study showed that conversation doesn't just slow you down equally in all directions. It disproportionately makes that downward sluggishness much, much worse.
So it takes an existing weak spot and just hammers it.
It does. It creates what the source material called a shitty, a fatal angle, a critical vulnerability.
And what does that mean for an average driver on their commute?
Well, think about typical road hazards. Potholes, debris on the road, a small animal, maybe a pedestrian stepping off a curb right in front of your car.
They all appear in that lower visual field.
Exactly. So you have this combination. Your brain's resources are being stolen by the conversation, plus your natural slowness to react downwards is being amplified. It means your ability to respond to immediate ground-level danger is it's decimated when you're actively talking.
Wow. That really elevates this from a general warning to a very specific mechanism of danger. It tells exactly why hands-free talking leads to more crashes. So let's tie this all together. What does this mean for all of us? We started with the hands-free myth, and it seems the real issue isn't a slow foot on the brake.
No, that's just the final symptom. The delayed braking is a consequence of the problem, not the problem itself. The problem starts way earlier with degraded visual processing.
The core finding seems to be that active conversation creates this fierce battle for brain resources.
And it directly interferes with the basic neural processes you need to aim, move, and control your eyes accurately. If your eyes can't scan and stabilize efficiently, your brain can't even begin to recognize danger in time.
So the practical takeaway for you listening isn't that all audio is bad. It's about recognizing the mental cost of actively creating speech.
Right. A light chat might be fine in simple conditions, but the moment you're asked to do some heavy mental lifting, planning something, debating, retrieving a complex memory, you are borrowing resources directly from your road safety budget. Especially in tricky situations. Merging onto a highway, navigating a busy street. In those moments, the science is clear. Prioritize your visual attention, keep the mental chatter to a minimum. You need those eye movements to be at 100%.
This research was so insightful. But it does leave us with an interesting unanswered question. They proved talking is disruptive and listening is not.
Yes, but they couldn't quantify the exact threshold. How much cognitive load does it take to trigger this breakdown? How difficult does the conversation need to be?
Does an emotional conversation have more impact than just recalling a fact?
That's a great question. We don't know.
Which raises a final thought for you to consider. If simply listening is safe but active, demanding thought is dangerous. Where exactly is that line? How complex does a thought have to be? Or how much effort do you need to put into a conversation before your eyes are no longer working at full capacity? That's the question to mull over the next time you find yourself planning your entire week while approaching a tricky intersection.
And that's a wrap on this episode of MedDecode. I really appreciate you joining me today. If something we talked about sparked your interest, or if there's a medical term that's been bugging you, let me know in the comments. And if you enjoyed this, be a pal and share it with a friend. We'll catch you on the next one.